Hello and most welcome to 1299 in the Heidegger series. It's still a bit dark here, but we're approaching a wondrous morning, and I think we could expect a clear sky. It is definitely very chilly, around 10 minus, but crisp and not as slippery as yesterday, when I had a misfortune of actually falling. We will continue today with A Single Universe by Roberto Unger and Smolin, and we are at the section of Smolin, and it is not as demanding as I initially thought. The style of Smolin is lucid and clear, although the subject is the most difficult I ever encountered, I would say. When it comes to understanding, it takes a lot of time. And I would say it's the Seinsfrage of Heidegger expressed in a more understandable way, so it doesn't elude realization, which is, as you can understand, very promising. I will continue where I left off in 1298. And I was talking about diffeomorphisms and how general relativity physical events are defined relationally and contingently in terms of physical effects perceptible there. The use of diffeomorphism in general relativity serves as an example of a general method for eliminating background structure, which is to introduce a first kinematical level of description, which is encumbered by background structure, and then to reduce the description to those engendered by a system of relations by defining physical observables to be those invariants under the action of some group acting on that background structure. This is called gorging away the background structure. Three major examples of this are local gauge transformations in Maxwell and Yang-Mills theory, space-time diffeomorphisms in general relativity, and reparameterizations of the string world sheet in string theory. This may seem like an awkward and indirect way to proceed, but it allows us to write simple local equations of motion for fields. This would be much more difficult once the naive local fields are eliminated, because they are not gauge invariant. Indeed, in all three cases, all the physically meaningful observables are non-local. Two relational paths to general relativity. Einstein and shape dynamics. Since the important work of Stachel and Barber and others, the interpretation of general relativity as a relational theory and the key role of space-time diffeomorphism in wiping out background structure are well known and appreciated. But recently there is a new development in the interpretation of general relativity, which is highly relevant for the nature of time, which is shape dynamics. This gives a different way of defining general relativity by gauging away background structure. In the old way developed by Einstein, space and time are treated on an equal footing. Spatial temporal coordinates provide a background structure which is gauged away by imposing space-time diffeomorphism invariance. Indeed, one of the things that is gauged away in this story is any distinction between space and time. Because there are space-time diffeomorphisms that will turn any slicing of space-time based on a sequence of spaces into any other. This means there is no meaning to simultaneity. Barber has emphasized for years that there is a nagging flaw in the beauty of this story. This resides in the fact that there is a big piece of background structure that is preserved in general relativity, which is an absolute scale for the size of objects. We must assume the existence of fixed scales of distance and time, which can be compared with each other across the universe. In general relativity, two clocks traveling different paths through space-time will not stay synchronized. Excuse me, just but the sizes will be preserved. So it makes absolute sense to say whether two objects far from each other in space-time are the same size or not. You can gauge away this background structure on top of the space-time diffeomorphism invariance of general relativity. But the result will not be general relativity. The reason is that imposing another gauge invariance changes the number of physical degrees of freedom. But the amazing thing is you can get to general relativity by trading the relativity of time of that theory for a relativity of spatial scale, so that the number of gauge transformations and hence the counting of physical degrees of freedom are unchanged. The resulting theory is called shape dynamics. Shape dynamics lacks the freedom to change the slicing of space-time into space and time. Consequently, there is a preferred slicing, that is, a preferred choice of time coordinate that has physical meaning. This means that there is now a physical meaning to the simultaneity of distant events. But physics on these fixed slices is invariant under local changes of distant scale. Shape dynamics is not actually a new theory. It is for the most part just a reformulation of general relativity. Its preferred slices are expressible in the language of general relativity, and indeed were already known to specialists of classical general relativity. They are called constant mean curvature, CMC, slices, because certain components of curvature are constant on each slice. The technical statement is that shape dynamics is equivalent to general relativity so long as the space-time has such slices, and most of them do. This is modulo space-time with black hole horizons, the interiors of which may be different in shape dynamics than in general relativity. You might object that these preferred slicings represent a return to a Newtonian conception of absolute time. But they do not, because the CMC condition is a dynamical condition, so that which slices satisfy it depend on the distribution of matter, energy, and curvature throughout the universe. Moreover, because the predictions of shape dynamics match those of general relativity, these preferred slices cannot be detected by any local measurements. The slices nonetheless play a role. Which can be seen in how the Einstein equations enjoy an impressive simplification when expressed in terms of them. Shape dynamics, just by its existence, has two important implications for the present argument. First, the impressive empirical success of general relativity cannot be taken as evidence for claims that the universe is fundamentally timeless, or even that there is no preferred simultaneity of distant events. These common claims are nullified by the fact that there is an alternative formulation of general relativity that does feature a preferred simultaneity. Second, the preferred slices of shape dynamics gives us a candidate for a global notion of time needed to provide an objective distinction between past, present, and future, and hence makes temporal naturalism a possible position to hold, consistent with current scientific knowledge. Relational purism. A relational purist believes that once background structures are eliminated, physics will be reduced to a description of nature purely in terms of relationships. An important example is the causal set program, which aims to develop a complete theory of quantum gravity and hence nature on the basis of an ontology of discrete events, the only attributes of which are bare causal relations. These are bare in the sense that event A is a cause of event B is a primitive. The causal set program denies there are any further properties. P of A, Q of B, such that P of A causes Q of B. The aspiration of the causal set program is to construct the geometry of a Lorentzian space-time approximately satisfying the Einstein equations as emergent only from a discrete set of events and the back-causal relations. To date, this has not been realized except in trivial cases where the causal set is constructed by randomly sprinkling Minkowski spacetime with discrete events. In pure relationalism, a role for intrinsic properties completion of the program of eliminating background structures does not imply that there can be no further properties of events. Except for the causal and other relations with other events. In an event's ontology, you may eliminate all background structures as the causal set program very nearly does, and still be left with an event having properties which are not specified when you know all the relations with other events. We can call such properties intrinsic properties. Intrinsic properties can be dynamical in that they play a role in the laws of motion. For example, in an event's ontology, energy and momentum can be intrinsic properties of events. They can play a role in dynamics and be transferred by causal links. This view is realized in the energetic causal set framework, according to which momentum and energy are fundamental and intrinsic and defined prior to space-time. Indeed, in this approach, dynamics is formulated strictly in terms of momentum and energy and causal relations. Position in space-time is emergent and comes in at first just as Lagrange multipliers to enforce conservation of energy and momentum at events. Dynamical pairings and relational versus intrinsic properties. I would like to argue that it is natural to suppose that energy and momentum are intrinsic in a world in which space and time are relational. This is based on the fact that physics has a particular structure in which space-time variables are paired with the dynamical variables. Momentum and energy. This dual pairing is expressed by the Poisson brackets. Here is a footnote to clear out some terminological confusions. Intrinsic versus internal. If a property of an event is intrinsic, it can be defined without regard to any relations to other events. That does not mean it plays no role in the dynamical equations of the theory. Let us reserve the term internal for a property of an event or a particle that plays no role in the law of physics. Momentum can be intrinsic, but it is not internal. Qualia are intrinsic and appear to be internal. Structural versus relational. By structural properties, philosophers seem to mean the same thing that we physicists mean by relational properties. I prefer the term relational, as structure seems to denote something static and hence timeless. A structural property seems to be one that transcends time or history, but temporal naturalism asserts that there may be no such transcendental properties of nature. Structuralism seems to be a form of temporal naturalism, which asserts that what is real, really real, are structures which transcend particularity of time and place. I think I will reread the previous section because it's getting very intense and interesting. Dynamical pairings and relational versus intrinsic properties. I would like to argue that it is natural to suppose that energy and momentum are intrinsic in the world, in which space and time are relational. This is based on the fact that physics has a particular structure in which space-time variables are paired with the dynamical variables, momentum and energy. This dual pairing is expressed by the Poisson brackets. And has its most profound implication in Noether's theorem, which says that if there is a symmetry of physical system under translation in a physical spatial coordinate x, then the corresponding momentum PA is conserved. Moreover, in the canonical formalism, PA is the generator of translations in XA. This can be interpreted to say that if a position is absolute and so has symmetries, then the corresponding momentum PA can be defined relationally in terms of translations in XA. But note that if space is defined relationally, then there can be no perfect symmetry under translations in a space coordinate. The reason is that the identity of the indiscernibles rules out symmetries, because a symmetry is by definition a transformation from one physical state of a system to a distinct state which has identical physical properties. But Leibniz's principle asserts that no system can have two distinct identical states. So if space is relational, we lose the relational definition of momentum as the generator of translations. So if space is relational, momentum can be intrinsic. We can also turn this around and take the view that momentum is the primary quantity and is intrinsic, and define position relationally as the generator of translations in momentum space. This is the point of view taken by the framework of relative locality. Adding intrinsic momentum and energy variables to the causal set description has an immediate advantage, which is to resolve a long-standing problem with a purist causal set approach, which is to get a low-dimensional space-time to emerge from a network of pure causal relations. So I would like to propose that generally we take momentum and energy as intrinsic quantities defined at the level prior to the introduction or emergence of space-time. Ever since Einstein began working on unified field theories, generations of theorists, down to the late 20th century string theorists, have speculated that progress is to be achieved by reducing the right-hand side to geometry as well, so that physics can be expressed in a purely geometric structure. But perhaps that is mistaken, which would account for its not having worked definitely. Instead, we can posit that it is the left-hand side that is emergent from a more fundamental description in which energy and momentum are among the primary quantities. Excuse me. Instead, we can posit that it is the left-hand side that is emergent from a more fundamental description in which energy and momentum are among the primary quantities, perhaps along with causal relations. The Newtonian paradigm, from the viewpoint of temporal naturalism, we can summarize the last few points by describing the proper role of the Newtonian paradigm for a temporal naturalist. On cosmological scales, the universe is unique and laws evolve, so the Newtonian paradigm breaks down. On fundamental scales, events are also unique. So the Newtonian paradigm breaks down here also. Events are distinguished by their relational properties and thus must be fundamentally unique. There can be no simple and general laws on the fundamental scale. Repeatable laws only arise on intermediate scales by coarse graining. Which forgets information that makes events unique and allows them to be modeled as simple classes which come in vast numbers of instances. Hence, the Newtonian paradigm works only on intermediate scales. We can also see from this that intermediate scale physics must be statistical, because similarity arises from neglect of information. It is interesting to wonder whether this might be the origin of quantum uncertainty. That is, the hidden variables needed to complete quantum theory if we are to explain why individual events take place must be relational. They must arise in adding the information needed to distinguish each event uniquely from all the others. Note that because the question of distinguishing individual events from others requires a comparison with others, such relational hidden variables must be non-local. Finally, it may happen that uniqueness might sometimes not wash out on intermediate scales, leading to a breakdown of lawfulness arising from novel states or events. This idea is developed below as the principle of precedence. So we're in chapter 3 of Smolin, page 393. It's getting more exciting. The setting, the puzzles of contemporary cosmology. The crisis of contemporary physics and cosmology begins with the triumphs of the standard model of particle physics and its counterpart in cosmology. The crisis arises out of our failure to go beyond the successes of these models to a deeper understanding of nature. As I will argue in detail, these failures have a common cause, which is the breakdown of the Newtonian paradigm when faced with the cosmological questions. The questions left unanswered by these models then serve as the primary challenges to the science framed by the new cosmological principles we have just outlined. The message of the data from particle physics. What we know about the elementary particles and forces is neatly summarized in the standard model of particle physics, which has been tested by numerous experiments since first proposed in 1973. As of this date, experiments at Fermilab and CERN have so far failed to discover any phenomena not accounted for by the standard model. The standard model describes the strong, weak, and electromagnetic interactions in terms of gauge fields, whose dynamics is determined by the gauge principle. More specifically, it is a quantum Yang-Mills theory coupled to chiral fermions. And Higgs scalar fields. Two principles that may be derived from mathematical consistency, perturbative renormalizability, and unitarity, restrict us to this class of theories in 3+1 space-time dimensions. There are plausible arguments that this kind of theory would emerge from a much more general class of theories at energies low compared to the fundamental scale. A key issue is that there is a great deal of arbitrariness in the standard model, even given it is a Yang-Mills theory. Three different kinds of choices must be made to get from the general class of gauge theories to a particular model. The theories first specified by fixing the gauge group. In the case of the standard model, the gauge group is GSM equals SU. The next choice is to pick the representations of that group that the matter fields come in. The standard model has 3 generations of fermions in a particular representation of G, and in SU, doublet of Higgs. The principle of mathematical consistency imposes some constraints on this choice due to a phenomenon called gauge anomalies. Very important. But this is one of an infinite number of possible consistent choices. Another somewhat selective principle is also satisfied by the standard model. This is that the theory is classically conformally invariant and cheerily invariant. With an important exception, which is the Higgs scale. As a result, all the coupling constants but one are dimensionless numbers, and all the masses come from spontaneous symmetry breaking. One then has to specify the values of all the coupling constants allowed to the theory by the principle of perturbative renormalizability. In the case of the standard model of particle physics, that is 29 dimensionless parameters, counting the masses and mixing angles of the neutrinos. There appears to be no principles of consistency which limit these choices within wide ranges. We have no understanding of why the particular choices we observe were the ones made. For each of these 3 choices, we require sufficient reason, and we don't have it. There seems to be no reason so far put forward for the choice of the gauge group and representations. we come to the choice of the parameters of the standard model. We face a very peculiar situation, which is that the actual values appear to be highly unusual or unnatural in two senses. Many of the dimensionless parameters are very small numbers. This strongly suggests a non-random distribution. These include the fine structure constant, the cosmological constant, the quantum chromodynamics, and weak scale in ratios to the Planck units, and the couplings between the Higgs and the fermions that determine the fermion masses. This is called the hierarchy problem. These unnatural choices are responsible for the very wide range of strengths and ranges of different forces. These in turn make possible a universe with complex structures over a very wide range of scales. Many of the couplings appear to be finely tuned to give a universe with far more structure than would be present with random values of the parameters. Our world has long-lived stars, supernovas, a mix of helium and hydrogen, and on the order of 100 stable nuclei with a wide variety of chemical properties, including carbon and oxygen, necessary for organic chemistry. None, and this is incredibly important, none of this would be true were many of the parameters not fine-tuned to special values. This is called the special tuning values problem. The hierarchy problem and the special tuning problem pose unique challenges for proposing a sufficient and scientific reason for the laws of physics as we find them in our universe. the message of the large-scale astronomical data. Let us now turn from particle physics to cosmology, where we find similar issues of hierarchy and fine-tuning. The data tells the story of a universe with structure and complexity over a very wide range of scales. To interpret it, we can rely on cosmological models, which are based on known physics. A model is not a theory, but it is very helpful as it tests how much of the data is explainable by known physics and how much remains for a combination of the initial conditions and new physics closer to the initial singularity. The restriction to known physics can take us back to an era when the temperature was as high as that so far probed in high energy experiments. This is a time before nucleosynthesis, but after the era when inflation is usually conjectured to have occurred. We will discuss inflation later as a hypothesis which is posited to explain features of the initial conditions for the models. On the largest observable scales, the history of the universe appears to be well approximated by a Friedman-Robertson-Walker model, which is a homogeneous and isotropic solution to the Einstein equations, coupled to matter. The model has several parameters, including a positive cosmological constant, and the matter involves at least 3 components: electromagnetic radiation, baryonic matter, and dark matter. As in all homogeneous models, there is a preferred cosmological time coordinate. very remarkably to within experimental accuracy, and the spatial curvature of the constant time surfaces appears to vanish. If there is a radius of spatial curvature r, it is greater than the present Hubble scale. Even at this very rough level, there are remarkable features of the data that suggests the initial conditions were very special. In addition to the vanishing of the spatial curvature, these include the fact that the cosmological constant is extremely small for a fundamental parameter of the laws of physics. In Planck units, it is 10 down to 120. These also include two coincidences of timescales, which concern the times of transitions between eras when different kinds of matter dominate the expansion rate. The first is that the transition from radiation to matter domination took place roughly at the time by Big Bang, when the electromagnetic field decoupled from the matter because the universe had cooled sufficiently for atoms to form. The second coincidence is that the present age of the universe, T, now appears roughly to be the crossover time, Tc, from matter to cosmological constant domination. Another very unusual feature of the initial conditions is that the universe must be modeled as starting off very hot, where the matter is concerned, but very cold when gravitational radiation is concerned. Out of the infinite number of solutions to the Einstein equations, which show a universe expanding from an initial singularity, the data suggests that the simplest surface, which are featureless solutions that are homogeneous and isotropic. This means that there are no gravitational waves initially. So all gravitational waves that are detected can be assumed to have been radiated by matter sources. A pedagogical tool that can be taken here is to think of affordances. As just shown here, if you go down and make things too definite, too small, too distinct, they will not add up. And that's why Newtonian physics is not working on an intermediary scale. See it as this instead, that there is a fluctuation between the two sides, measuring and measured. And this is why the idea of, I don't know what to call them, the definite, distinct objects of measurement or whatever, very hard to find a definition. But I think you have a feeling for it. See this as flexible instead. It is moving on this scale. And I took it up earlier when I spoke about the cut. The cut, and now clumsy expressions comes in, like observer and observed. They are only vaguely helpful in the beginning, or we don't have much choice, but they do obscure what is happening. See it as a cut. And I like to see the verbal thing here, the action of cutting, that is observer and observe. That is reality. That is reality. But if you put it here and an I here, that builds for confusion or inconsistencies. So this is the moving here, the action of movement. And J. Gibson said there are no objects and there are no one observing them that is distinct and apart. Neither are they conjoined. It is in reality itself differences evolves. They are not static, out there, so to speak. Or in a Tegmarkian sense, always there. I will continue with the Smolin to sort of further explain this. This is a rather large article called A Perspective on the Landscape Problem. This will help to explicate what I just went through. A second, I will be coming in. A perspective of the landscape problem, a first take on Lee Smolin's paper. I will read the abstract. I discuss the historical roots of the landscape problem and propose criteria for its successful resolution. This provides a perspective to evaluate the possibility to solve it in several of the speculative cosmological scenarios under the study, including eternal inflation, cosmological natural selection, and cyclic cosmologies. What is the landscape problem? The landscape problem in string theory was born in 1986 when Andrew Strominger discovered that there were vast numbers of consistent string vacua, many more than the Calabi-Yau solutions, which had been discovered the year before. As Strominger wrote in his paper describing that discovery, the class of supersymmetric superstring compactifications has been enormously enlarged. It does not seem likely that these solutions can be classified in the foreseeable future. As the constraints on these solutions are relatively weak, it does seem likely that a number of phenomenologically acceptable ones can be found. While this is quite reassuring, in some sense, life has been made too easy. All predictive power seems to have been lost. All of these points to the overwhelming need to find a dynamical principle for determining, which now appears more imperative than ever, determining which theory describes nature. However compelling this now seems, it took 17 years till 2003 for the landscape problem to be widely appreciated. Why was the existence of the landscape problem so hard to accept? Part of the answer is that many of us believed in the possibility of a principled explanation for the laws of nature. We hope to discover a short list of principles which could be realized in a unique theory, which would retrodict the standard model and uniquely predict the physics to be discovered beyond it. It was reasonable to guess that these principles would be the conjunction of those of quantum theory and general relativity. Given the difficulty of making any theory that combine them, the shocking implication of the results Strominger reported in 1986 was that this was not to be. At least within the confines of string theory. Given the implications, it is not surprising if it took until 2003 for many researchers to give up the notion of a uniquely predicative string theory. String theory offered more, however, than just a vast or infinite list of possible low energy effective theories. It offered the promise of a setting in which the different perturbative string theories are realized as expansions around solutions of a still more fundamental theory. Within that theory, there could be non-perturbative processes that would result in dynamical transitions between the different perturbative string theories, hence between different low energy phenomenologies. That more fundamental theory would have to be background independent by definition, because it would have to be defined in a way that transcended perturbative expansions around particular semi-classical solutions. Unfortunately, so far that promise of a truly background independent formulation of string theory has not been achieved. The reasons that this project, often called the search for M-theory, has so far frustrated would seem to be the subject or another review. But the landscape problem and the problem of background independence are closely linked. The former is the only route, the latter has to experimental confirmation. It is also the case that the background independent theory provides the setting for dynamical processes by which the universe can evolve through sequences of effective theories. Hence, the options for resolving the landscape problem are going to influence what we expect from the solution to the background independence problem. Below, I will suggest that this influence takes us to surprising places, altering fundamentally our strategy and expectations to construct the background independent theory. To get there, we begin by reviewing the landscape problem. Our aim will be to put it in a broader setting, which will give us a perspective from which to discuss the status of attempts to resolve both the landscape problem and the problem of finding a background independent formulation of string or M theory. The hypothesis underlying all approaches to the landscape is that there is a cosmological setting in which different regions or epochs of the universe can have different effective laws. This implies the existence of space-time regions not directly observable, because there is good evidence against the variation of the parameters of the standard model on scales of billions of years. These regions must either be in the past of our Big Bang or far enough away from us to be causally unrelated. These different possibilities give rise to three classes of cosmological settings in which to situate hypotheses for the dynamical evolution of effective laws. 1. Causally distinct regions, which may be called pluralistic multiverse cosmologies. The main example of these is eternal inflation. 2. A succession of past epochs, which are cyclic cosmological models. Recent examples are ekpyrotic models of Steinhardt, Turok, and colleagues. And the conformal cyclic cosmology of Penrose. Three, combinations of the two, in which there are epochs in the past which branch on reproduction. Examples of these are Phoenix cyclic cosmologies and cosmological natural selection. Attempts to solve the landscape problem have so far been situated mainly within two of these settings, which are an eternal inflation and cosmological natural selection. One of the aims of this essay is to give an evaluation of how well each attempt is doing. Another is to provide a deeper perspective that might guide the search for new solutions to the landscape problem. But before we discuss details, it is worth stating carefully what exactly would constitute a solution to the landscape problem. An acceptable solution to the landscape problem would be an explanation for the choice of effective laws and their parameters observed in our universe, which is scientific in the sense that that explanation has several further necessary consequences, at least some of which are falsifiable by presently doable observations of experiments. Two, it will have other consequences which are strongly confirmable by presently doable observations or experiments. By strongly confirmable, I mean that the consequences are sufficiently unique to this explanation that if seen it would constitute strong evidence for the correctness of the explanation. Some of the falsifiable consequences have failed attempts at falsification, and some of the strongly confirmable consequences have been confirmed. The solution should explain the improbable features of the standard model, which include the large hierarchies in scales and dimensionless parameters, and the fact that they seem to be fine-tuned to create a universe that has highly improbable complex structures over a wide range of scales, from clusters of galaxies down to molecular biology. The solution should explain the very special initial conditions of the universe as well, given that a solution to the landscape problem requires a speculative cosmological scenario. If confirmed, there will not be an opportunity to go back and adjust it to explain also the choice of cosmological initial conditions. And I think that could serve as a primer to the landscape problem. Yes, it's very hard to understand as of yet, but use this as a picture, and helpful could be if you have all these small things that whose size is not decided by this process, then you will have a measurement problem. And you will say these are coming from the landscape, the background. So this is an enormous specification of the problem of the world at large, as Thomas Nagel would call it. and it's a much more precise and clear definition of what he would have meant. He was just looking at the world at large, not really seeing it starts here, it starts with the measurement problem. We need to refigure what is measuring. That is the problem. Not how we measure or the exactness of measurement, but what is measuring. This is the problem here. And of course this has connection to making math into something it is not, which I come to the conclusion is killing off math, making it an obstacle rather than a helper. And constructive mathematics is showing to that direction, that the Platonic tendencies, which are completely useless in physics, are still ghosting, showing their spectre. Most interesting. Thank you very much and have a very pleasant morning. Bye bye.